Get your clickers out, and we'll do 2 clicker questions today. So that's good. Here's our basic outline. I have a few housekeeping things to do before we get down into the nitty gritty. Where are you going? Oh, wrong class? Oh, it happens. Anyways, yeah, first thing, we have some SI information. Now, Yasmin went over this already last time. Here it is again. And I set up a SI page in web courses. So, you know, we're going to have it in several different locations. Move on up to the front, not so far back. Good. Nice. Good. Anyway, so today is Thursday. So pretty much right after class, just mosey on over to Nelson School of Communication 114. Is that a classroom or the lecture hall? It's got to be a classroom. Does anybody know?
It's a normal size classroom.
All right. All right. So get going on that, and we'll have this on the first slide of lecture every day, and in web courses, as I say, and I think Yasmin will probably post it in discussions. Now, there's some new rows in your grades page that I want to go through with you in relation to getting your iClicker 2 registered. By the way, actually, let me pause the. Now, in regard to that, here's the 2 new rows, actually 3 new rows in your grades page, 1 for each day that you register early. So if nobody registered early for Monday, I mean, we had a clicker question and nobody was on the roster by then, but hopefully today, a bunch of you will be on there. And there's a slot for next Tuesday, and then next Thursday. So what you want to do is you want to register in web courses only. Now you can register at iClicker.com for another class, but not for this class. They won't conflict, but you must be registered through web courses. Otherwise, it will not show up, and you won't get any points when you need them for the regular part of your grade. Missing a bonus point is one thing. It's no skin off your nose, but when you start missing participation points, and that starts on January 22nd. Question? Got to do it again. What is your first and last name? Caldwell Grenier. Do you have to dash out to class right after this? Okay, why don't you, well, the reason I say that is if you come up after class, and hopefully we'll dismiss a few minutes early, come up and we'll double check to see if you're on the, because there are a few people that are on the roster, but I don't recall your name, but I'll be able to check it. Anyway, so you go to this link, the iClicker link, in our web courses area, and when you do that, you'll get and when I synchronize the roster and everything, you'll get a bonus point if you're in class. I mean, if you click in during that class. If you don't click, then All right, so get that done as soon as you can, and hopefully a bunch of you will get a few bonus points between now and January 22nd. So, any questions about that? Okay, let's keep going. I want to talk about our textbook website, and I had a few students ask me about it, and apparently, this is the textbook website right here. Um, and so when you go, if you buy, if you go to kendallhunt.com, or if you go straight to this page, either one, um, this is where you're going to go to every day and sign in and read the book if you decide you want to buy the book. But apparently there are no spring 2019 sections set up yet as of last night anyways. But I put a message through on email, and hopefully they're doing it right now as we speak. But that'll be set up in the next day or so. So keep your eyes open, and what I will do is give an alert in discussions, saying, and actually somebody's already started a thread, I think in this class, yeah, about, what's happening. And I said, just hold off until we get the section set up. A few of you have set up in fall semester 2018 sections. Don't do that. All right. Just resist the urge. We'll get you in there soon enough. If you've already done it, it's not a big disaster. It's just a tiny disaster, and we'll just get you squared away on that without too much fuss or muss. But if you haven't gotten it, if you want to get the book and you haven't registered yet, just hold off a little bit longer, okay? Questions about the textbook? Okay, let's keep going. I want to give you a little bit of um, instructions about how to use discussions. Now, here's a discussions post from a student a year ago, actually, spring of 2018. How do you get an iClicker? Where do I buy an iClicker? And I want to give you some instruction on how to use the discussions tool. First of all, post your questions and comments and discussion. If you have something about a homework assignment or a test or something from the notes, post a query in discussions, and one of your classmates will chip in and answer or give you some tips. And a lot of times, or Yasmin will do that, and I'll do it. Depend whoever gets there first, and I'm in there a lot, so any, as I mentioned before, any topic other than your personal grades, etc., is appropriate there. Don't send me a course. I don't want to be mean or anything, but don't send me a course mail message in the inbox messaging system through web courses. Okay? Because I'll just tell you, go to discussions, repost this in discussions, and I'll answer you there. Because like if we have a tricky homework problem or something, I'm going to get 90 messages like that, and that's going to be very inefficient. But if if you post in discussions, everybody will be able to see anything that I say, anything that Yasmin says, anything that the grader says, anything that your classmates say that is helpful, hopefully, and without having to, burn up my electrons on the internet with 90 individual messages. So do that, and things will be righteous. Don't put your phone number in there either. And and every semester there's temptation to do this group me business. And I have to give you an admonition about it. We've busted people for cheating on exams using group me, and I highly caution you about that. All right, but I know it's popular, so that's up to you, whatever you want to do. But I would caution you about it. Now, I want to draw your attention to this little area down below. When you start a new thread, there's a couple little options that you can check off or leave unchecked. All right, down towards the bottom. There's the title, and then there's the actual text that you type in, and a bunch of these, up here, these formatting icons. You can actually type in equations. See if I can do it. One of these, I can't really see over there, but one of these in the second row is for doing equations. I think it has square root of x in it or something like that. Those equations are really, really nice. But it takes a little bit of getting used to. But anyways, I want to talk about this stuff down here in the red fuzzy box here. Um, so there's a close-up. Now, the first thing I want you to do is check to check allow threaded replies. Because if you don't, and there's a lot of people contributing to the thread, it becomes mayhem. And in if you're trying to work on a homework problem and figure out a solution, there's a lot of people, I don't know what to do, and that. But if you get it threaded, you can follow somebody that's got a clue and follow their responses and stuff. Okay, whether that's me typing a good reply or someone else. So do that. Allow threaded replies, and things will stay a little bit more organized. The other thing that's helpful is to allow liking. All right, and that will also help us signify helpful responses. All right, so you'll be able to see if people like it. And it's not like Reddit where you can give it an upvote or a downvote. So you can't see any downvotes in Canvas, but at least you can see if somebody likes it. All right. So, and then the other thing is when you first start it, the title of your thread, don't make it just help me. I mean, I know that's how you might be feeling, but what I want you to do is type in help me on homework 7. How do I get this acceleration in number 4? Make it descriptive, and then it'll be efficient for your classmates and for you actually to refine your the topic and see if it's helpful to you. So if you follow these instructions, then discussion groups can be a real helpful virtual study group. Some semesters, it's a real beehive of activity. And I hope this is one of the semesters where it becomes a beehive because, the way that you learn and become really sharp is through interacting with other humans. The more interactions you have with humans, the more you learn. And discussions can be important. Study groups, SI, office hours, lecture. Now, lecture, you're not really interacting, you're just listening right now. Okay? But when we click, that's a way for me to force you to think about stuff. And some of them won't be that hard. Some of them you'll definitely find them challenging. So let's get some clicking done. So take your clicker out. And I have a totally bodacious scientific question. You all got your clickers ready? Turn it on. Oh, you know what else? I see a guy up here on the left side of the class kind of shaking his clicker. If you just bought it or if you just rented it, go and get some Duracells and put them in the back, because the batteries that they come with are horrible. They're El Cheapo batteries, and they'll flake out on you in the middle of a test. I mean, and so in the middle of the test, you definitely don't want to, have your clicker come up zip zap. All right. So try to remember that. Now here's our ultra difficult scientific question. Which individual here is the toughest of them all? So this is just kind of a goofy question, just for practice. And I'm going to answer as well because I know the answer to this, and I bet in fact, I can almost guarantee that you guys do not. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Um, and let me stop it. Yeah, nope, not on multiple choice. Yeah, just hit the letter and you're good. If you get a check mark, that means I got it. That means got it. Dr. B's got it. That means you're not on the frequency. You have to, if you came up with Go Nitro, then it, it'll say you'll get a check mark, but it doesn't persist. You'll get it for like 5 seconds, and then it'll just say ready again. And you know why? The reason for that is you could change your answer. You can, I mean you can't do it now because I stopped the question. But you can, before I stop the question, you can change it and type in, letter E instead of letter A, or whatever. Same with numbers and symbols. And we're going to do some numbers here in a second. So yeah, you can actually change it, and that's why it says ready. I'm ready if you change your mind. All right, but if you get that check mark, that comes in after you click the send button. And if you get that and you're happy with what you clicked, you're golden. All right. Now, uh, let's just take a look at the results here. Here we go. There are the results. Most people voted for B, Chuck Norris. And what? Somebody voted for Barney the Purple Dinosaur? Oh my goodness. I'm not sure I'm getting through to you guys. But luckily nobody voted for Justin Bieber. But you know what the correct answer is? Bruce Lee. Bruce Lee, by way of historical footnote, is the only guy that's ever beat up Chuck Norris in the movies. 1972, The Way of the Dragon, when Chuck Norris was young. So yeah, technically, the one guy known in the known universe. What's that? What's that? Well, yeah, Godzilla, but the thing is, Godzilla is yes, Godzilla, but he's usually up defending Tokyo. He's helping him out there. It looks like he looks like he's destroying Tokyo, but he's actually just helping Tokyo. So Bruce Lee, Bruce Lee is everywhere. So uh, uh, that's the mystery of the Godzilla movies, I tell you. Anyway, so we're just messing around here with this question, but now we're gonna do another clicker question, and this is a serious question. So we're not gonna be doing any more Chuck Norris type activity here. But we're going to do a calculation. So now, when we go from multiple choice to numeric input, you have to hit the refresh key. All right. And the refresh key, and now I'm going to switch my question to numeric. Here's your question. Calculate the length of the hypotenuse of a right triangle. And then down here in this blue box with the blue outline, it says type in the numerical part of your answer to the nearest meter. Okay, so for instance, if your calculation reads 11.87, then type 12. And now you have to hit the send key. And now you got to hit the send key because Canvas or iClicker doesn't know if you're typing in 12 or 120 or 12,403, so you have to tell it when your answer's in and you're ready to send, so you hit the send key. And I'm going to do that myself. Oh, by the way, the way let's try. Okay, hit the refresh key again. It starts you out at the number 1 in the lower left. If you don't have the number 1, go ahead and hit your refresh key again, and then go up and down to get different numerals. Okay, so the next numeral up is 2, and then down below that is a 0, and I believe below the 0 is a minus sign. And then below the minus sign is a 9, 8, 7, 6, 5, 4, 3, 2, 1. And if you type in a 0 for your first letter, it automatically puts in a decimal point for you. That's nice. So actually, I'm going to do that. And then type a rightward arrow key, and you'll get another numeral, and you can, so I'm going to put in 0.3. You put in whatever you think is right. And yeah, so go to the right again if you want to type in a third digit, and then go find your digit. And yeah, and then hit the if you've got your number the way you like it, hit the send key, and it'll give you a check mark. Okay. Yeah, but that doesn't matter for clicking in class. Yeah, if you've did you click? Did you get a check mark?
Yeah, I did it.
All right, that's a separate task. Yeah, yeah, maybe try a Windows computer in the library or something. Yeah. Don't use Safari to register. Yeah, yeah. So Safari is shaky. Is that an iPhone? Yeah. So just go to the library and use one of those stinky Windows computers for 5 minutes. Yeah, but if you've got a check mark, that means you're good. All right. So, and you can. I'm gonna change mine. So let's see. Ooh, I'm changing it to 9.35, and I'm gonna send it. Okay, so I get a check mark. Okay. Anyways, good. I see 39 people. 10 seconds to put your number in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and I can look at pretty good. You guys did well. Let's double check the calculation. This is Pythagorean theorem. Right triangle. So go ahead if you're a little rusty on that, and it looks like a few of you are, which is all right. I'm gonna try to build you up. Every day a little bit more every day, step by step. I'm not gonna try to outdistance anybody. We have a whole wide range of mathematical skill and experience in this class. So matter of fact, raise your hand if you've had calculus. There's good. Yeah. See, there's a few that have had calculus, and there's some people that are just starting out. They haven't even taken college algebra yet. All right. So Pythagorean theorem. This is about as fancy as the trig gets. I mean, we're going to use this and maybe a little bit more, but anyway. So let's keep going here. So you put in your 8 and your 6 and you square them. Okay. And we're trying to get the square c squared for the hypotenuse. And then so 8 squared is 64, 6 squared is 36. Add them together, and you get 100. So c squared is equal to 100. Now, that's the square of the hypotenuse. What we want is c, not c squared. So now you hit the square root key on your calculator, or hopefully you know the square root of 100 is 10. Because 10 squared is equal to 100. And so your answer is 10 meters. And don't forget that the 10 meters squared inside the square root, or 100 meters squared inside the square root, you have to square it to 100, and you also square root meters squared. So your answer coming out of the square root is square root of 100, 10, and then square root of m squared, m. And then what you do is type in 10, and then you hit the send key. And 78% of you did that, so you did a good job with that. And we'll be using this in class and on exams to type in numeric answers, like for an acceleration, 2.305 meters per second squared, and you'll type in 2.305 and hit the send key. And hopefully that's the right answer. All right, so that's it for clicking today, but try to get your clicker registered and as soon as you can. And those of you guys that are already registered and you click today, I'll see it and I'll be able to check it right after lecture. And if I don't do it, I tell you what is your name again? No, Grenier, Grenier, yeah. First name? Coldwell. We'll just meet out in the hallway because there's another class coming in right after this, but we'll check it. And if you want to check your clicking right after class, we can certainly do it out in the hallway. All right, let's turn to our main topic for today. Look at this picture. You notice anything? What do you notice? No. Huh? The neck? Yeah, everybody's on their phone. They're all bent down at the. And your parents probably yell at you. Get your nose out of the phone. We're having dinner. Yeah, sometimes. So anyway, but I look at this and I think, this is what humans do. If you think about it, I mean, just step back and think about what everybody's doing there. They're reading. They're reading something. They're trying to learn something. And the thing about it is, this thing that we do, we humans, we're always trying to learn stuff. We're learners. That's in the Marvel Cinematic Universe. This is the learning planet. This is the planet. That's our superpower. We learn. And the thing is, you're trying to learn something, and the subtext of it is that you're trying to learn something that's true, and if you find out that it's false, you're ticked off. So, this thing that we do, we learn, we're trying to learn stuff that's true. And you think about the things that you do during the day, almost everything, this entire institution is dedicated to this quest in various forms. Now, science is a little different from other classes, but everything that we do, and you know what, you guys are, this is our superpower, really, if you think about it, because you're here because you want to be here, right? Nobody's required to be here at UCF. It's voluntary. You pay money. You take loans out to be here and to be in this quest. And even when you leave here, it's just a different place. You're still going to be on the same quest for truth. So let's talk about it. Truth is a judgment call. How do you judge what the truth is? If somebody, if you read something on your phone, or if you hear somebody say something, you read it in the newspaper or on the internet, and everything on the internet is true supposedly, but you still have to use your judgment. So how do you judge what is true? Well, let's look at the definition of the truth. Here's a classical question from the ancient philosophers, Aristotle and those cats. Does truth reside in the thing or only in the intellect? Well, here's what Aristotle answered. Here's a little sketch. Nobody knows exactly what he looks like, but supposedly he looks a little bit like that. Now, he's got a long answer. And if you've ever read any Aristotle, raise your hand if you've ever read any Aristotle in one of your philosophy classes. Very difficult to read. very wordy, verbal, to say of what is that it is not, or to say of what is not that it is false. While to say of what is that it is, or of what is not that it is not, is true. Now that's Aristotle making a fairly elaborate statement of, you know, what the truth is. It exists. It's an existential definition. Okay, now here's Augustine, another famous writer, and he's basically taking the same view. That is true, which is. All right. And another famous philosopher, Aquinas, Thomas Aquinas, this is the one that's actually closest to, I think, towards, you know, what this is more of a humanistic answer. The truth is that towards which the human intellect tends. And that's really saying that our quest, all of us as humans, is, you know, this thing toward which our intellect tends. It's a quest, and it's a quest for truth. And that it's what we're always looking for. Now, how do you recognize what the truth is? You know, what are the criteria for the truth? You know, just like, you know, you look at a $20 bill, and you know, or better yet, you're working at a 7-Eleven, and somebody gives you a $50 bill, and you got to check to see if it's counterfeit or not, right? Whether it's true 50 or false 50. And there's ways to check it, okay? Things you supposedly. All right. So now, in different pursuits in our human culture, things are different. You know, so the scientific enterprise, that's what we're about this semester. It's a totally different criteria, but think about this, a love letter. You know, everybody's seeking for that. And what you want to do is know that it's true. You know, just like this famous song, Barbara Allen. And there they twined in a true love's knot. Little low. The red, red rose and the briar. So, you know, you get a love letter from somebody. Hopefully, you're hoping that it's true. You want it to be true. And if it's false, you know, it's disappointing. Now, court of law. Another, you know, segment of human activity. Important. You know, you go in there, and in some way or another, you swear an oath to the truth. You know, how do they say it on Law and Order? I swear to tell the truth, the whole truth, and nothing but the truth. So that's an oath. And they have different criteria as well. Okay, so for instance, in federal courts, there's something called Rule 804 in the Rules of Testimony, and it's called exceptions to hearsay. Now, hearsay, if you ever watch CSI and Law and Order, Criminal Intent, and all this stuff, you know that hearsay itself is inadmissible in general, but there are exceptions. For instance, a statement under belief of imminent death. And that's considered admissible in a court of law because it's a deathbed confession. You know, and so the guy died on his deathbed, but the last thing he said on his deathbed, you can assume is true. And so, and that's because it's our judgment that if it's the last thing you're going to say, you're not going to be lying anymore. You're just going to say something that's true. Right? But you still have to check it and everything like that. And it doesn't necessarily win you your case, but at least it's admissible in a court of law. Here's another one. Statement against interest is admissible. So this is hearsay evidence, and if it's a statement against interest, that's like saying that it's something you would never say about yourself unless it's true. So you would never tell somebody, you know, how you murdered the I don't even know, your enemy. You would never say that unless it was true. And in the rule 804, it says, so contrary to the declarant, that's the person that's making it, the statement, so contrary to the declarant's proprietary or pecuniary interest, or had so great a tendency to expose the declarant to civil or criminal liability. So if somebody says that themselves, it's going to be admissible as something that you would never say unless it was true. All right, so those are, and you can look up other rules of evidence. And basically, it's the rules of evidence are how you put forward that which is true in a court, in a federal court system. State courts are a little differently, but they have rules about hearsay as well. All right, so this whole thing, this thing that we do, us humans, this quest for truth, every part of it, whether it's a love letter or a court of law or the scientific enterprise, they're all going to have some criterion to make a judgment call. Yep, that's true. Now, what we're going to be doing is figuring out Galileo's criterion of truth. And that's what we're going to be talking about for the next few minutes. Let me do something here. Okay. One of the things that Galileo wanted to be able to do was to predict the future state of a physical system. Like in his day, the military technology was not a B-2 stealth bomber, flying 7,000 miles and then coming back another 7,000 miles. For him, it was a cannonball. Where's the cannonball going to land? How long is it going to take to get there? Is it going to hit the ship, or is the ship going to be out of position relative to where the cannonball? So you got to figure out all. He had an interest in those days. Everybody had an interest in that, and it's a prediction of future state, sometimes out of chaos. Now this is the cover photograph for the textbook. It's a football game in California in the rain, and if you look at this picture carefully, I dare you to find the football. Look at that. Everybody's moving in different directions. Somebody in there's got the ball, but you can't really tell who's got it. They're running in different directions. They're looking in different directions. Somebody's got it in there. Very complex interactions. All right. And so sometimes you're trying to make sense of that. If you're, for instance, if you're one of the players in the defensive backfield, you're looking at that and you're trying to figure out who the heck has got the football. You're trying to, and then you're going to, if you can locate it, then you're going to try to predict the future state and intercept them. And whoever's got the ball, knock them on there. You know what? You tackle them if you can. So now, the scientist, as we said before, the scientist looks at the universe and he tries to answer questions about the things that he sees. He's trying to make sense. The grand book of nature. So for instance, is there a plan or a pattern in what he sees? This path that I've mapped out here for the path of a baseball or a cannonball or something, projectile motion, what's the pattern for it? What's the rule? What's the formula for it? And, is there a clear interaction of some kind between the baseball or the cannonball and anything else? Like the air, it might interact with the air resistance. What else does it interact with? Well, we now know that it's mainly interacting with the Earth, the gravitational field of the Earth. That's its main and dominant interaction. So there's the baseball. Here's another question. What will the future state be of the things that he sees. So in other words, if you start your clock down here at t equals 0.00 seconds, so you start your stopwatch, and then, how long does it take to get up to the top of the arc? And then how long does it take to get down to the bottom on the other side, as it goes down through the rest of the arc? So, we want to know that kind of stuff. And then we want to be able to tell somebody about it. And you don't want to just go event by event. What Galileo was able to do was able to make an expression. Here it is. This is an expression for the trajectory, the y component, the y coordinate of the motion of a projectile. Now, don't worry about that equation. It's kind of complicated, but you could take an eyeball look at it for now. And we'll take a little closer look at it in a second. And what Galileo was trying to do was say, all right, what is an acceptable or reliable answer to all those questions? What's an acceptable scientific answer to the quest for a pattern, or the quest to know a future state and predict a future state? Well, about 400 years ago, he proposed that, and we've already looked at this quotation, but let's just review it. Philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze, and it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, which we talked about last time, without which it is humanly impossible to understand a single word of it. Without these, one is wandering about in a dark labyrinth. So this is a statement of Galileo's conviction that truths about the physical, this basically defines the physical universe. Something that you can measure and something that has some kind of a mathematical backbone. And there's the mathematical backbone right there for the vertical component of motion of something in free fall. All right. This equation, we're going to start hacking into it here. This involves the positions on the y-axis. And look, so here, there's final y coordinate, y subscript f, and it's based on, if you want to find that, that's your future position, you have to start with your initial y subscript I. That's the initial y coordinate. All right, so that might be 0, or if you're up on top of a building, it might be 25 meters, or whatever it happens to be. Also, speed. This is the initial upward speed, the speed that you launch upward with. So if you have a straight pop-up, this is all your speed. But if you have a baseball hitting out to the outfield, you have a little bit of vertical and you have a little bit of horizontal speed as well. So this equation involves the vertical speed, the initial vertical speed. Also, the acceleration due to gravity. And believe it or not, triangles are going to help us understand this last, there we go. This last part here, 1/2 gt squared. You know what that is? That's 1/2 base times height. In a particular kind of a graph, it's not a right triangle, but it's still 1/2 base times height on a specific graph that we'll try to tackle on Tuesday. So all these things put together, this is one of the most basic examples of what Galileo expected to find. And he's the one that figured this one out. This equation of motion for a projectile. So let's take a look at some of the features of it. First, velocity. Velocity is defined as a speed and a direction. All right? So speed is the number on your speedometer. And if you're out on Alafaya and you're going 40 miles an hour, that doesn't tell me where you're going. Because you could be going north, heading for Walmart, or you could be heading south, heading for Waterford Lakes, at 40 miles an hour. So you have to also know the direction. And those two encode the motion of the object so that you can figure out its future state. So for instance, you can figure out its position at a future time and its velocity at a future time if you also know the velocity, how the velocity evolves over time, right? Does it get faster? Now, so you're out there on Alafaya. Do you travel for 5 seconds at 40 and then speed up to 45? And then, and then up to, now I know everybody in here is a nice, good citizen, and you never disobey the speed laws. But you know that people like that exist. And I'm not looking at anybody, but if you disobey the speed law and go 60 on Alafaya, you're probably going to be breaking the speed law. But, you're going faster. So this whole idea of going faster or slower over time is important to figure out where you're going to be in the future. How long is it going to take you to get to Waterford Lakes? How long is it going to take you to get up to Walmart so you can buy some mac and cheese that they sell at Walmart, okay? Or Publix. I wonder which is better, Publix mac and cheese or Walmart mac and cheese. Here's another thing that can evolve over time: direction. All right, you're heading down Alafaya for Waterford Lakes, but then you decide to dip over and get some wings at Bubbaloo's Barbecue. So you dip over to the left. Okay, and so that's if you're trying to figure out where you're going to be at a future time, you got to know that kind of thing as well. Now, all these things together are what we would call in physics equations of motion or time evolution equations. And we're if you've ever seen that wonderful movie Hidden Figures from a year or so ago, one of my absolute favorite movies, Katherine Johnson. Oh my goodness. We'll have a lot to talk about with Katherine Johnson. But what she was, and her dramatic, and that was all true. Well, most of it was true. Some of it I'm not sure about all the romance and stuff like that, but yeah, John Glenn, the famous astronaut, did ask for Katherine Johnson to verify the equations of motion for John Glenn's capsule. Is it going to land in the ocean, or is it going to skip off into space and he, becomes lost in space? And Katherine Johnson had to know the mathematical backbone of that physical system, the Mercury capsule carrying John Glenn. So this equation that we've got, here it is again, YF equals YI plus VIYT plus 1 half GT squared. You could call that the equation of motion for projectile motion for an object in free fall. This is the Y coordinate anyways, of an object in free fall on the surface of the Earth. All right, now, and the tricky part is, so this is fairly simple. All right, so if John Glenn were riding in, one of these things where they shoot a guy out of a cannon at the circus, when these guys on motorcycles, they take jumps, and then they land. Hopefully, they land safely on the other side. That would follow this equation. But John Glenn up in space, quite a bit trickier. Space capsule. But, you can do it. Now, for this one, for a projectile, Brett Favre throwing a football down the field, or Tom Brady throwing a football down the field. I hate the Patriots. The Cheatriots. But anyways, a football throw, a quarterback throwing a football down the field. Yeah, this is it. But you also need the equation of motion for the x coordinates. So and Galileo figured that one out too. And that's a significant equation of motion. It's a little simpler than this one, but they have to both. You have to have both if you're going to predict. And here's something that you may have seen on TV. If you're ever like watching TV on the weekend and there's no football and there's no basketball, sometimes there's golf. And if you're really desperate, you watch golf for a little bit. And some of these golf telecasts, they have a pretty cool device where they track at the tee shot, they take out their big, Tiger Woods takes out a big driver and he drives it, 300 yards down the fairway and stuff. And they track it. And they can predict where it's going based on, the initial trajectory of the golf ball. So that would be this as well. It's kind of cool. I forget what they call it, but some golf shows, they actually show the path of the ball. Ladies golf, men's golf, both. It's kind of cool. I enjoy looking. Usually golf is pretty hard to watch, but that part is interesting. So let's get down to business. Motion in 2 dimensions. All right, and 2 dimensions plus time. Time is the 4th dimension. So two spatial dimensions are like x and y graph paper. Piece of graph paper, x-axis, y-axis. And the 3rd dimension is, the vertical, the z-axis. And then the 4th dimension is time. And we'll be talking about that through the semester. Anyway, so let's look at point A and point B. Here you go. Point A and point B. It's as simple as you get. And you're studying the motion, how do you start with, how do you start figuring out the motion and predict a future state or an intermediate state? Where is it going to be 17 seconds after it leaves point A? All right, so if you know the endpoints, you might not know what's happening in the middle, the intermediate times. So let's take a look at this. First thing you do, and look at this animation carefully. Look at the background of the image. It's blank. So the first thing you do is you figure out a coordinate system. You break out the graph paper. All right? And then you put in good old x-axis and y-axis usually. But you can use curvaceous coordinates like, the latitude and longitude. Those are considered curvilinear coordinates. But graph paper is good, x and y. So then you label, there's the y-axis. You're down here, look at the animation. There's the x-axis. Okay, so you figure out your coordinate system and you just park it there. And, you have freedom as to where you put it. So I just put it down here. I could have put the origin at point A or point B or anywhere else. I just chose it down here. And then you got to decide yourself, well, how big do I make my graph paper lines? Do I make them meters, miles, or nanometers? A nanometer is a billionth of a meter. A billionth with a B. 10 to the minus 9 meters. Now, meters, miles, or nanometers. Meters are good for humans, human activities. Miles are good for cities, municipal time and distance scales. Atoms, nanometers, billionths of a meter, those are good for atoms and molecules and stuff like that, nuclei. All right, and we'll be doing some nanometer type activity a little bit later in the semester. But for now, let's just go with meters. All right. And then you start counting. You start counting blocks. And believe it or not, I counted all the blocks. Okay, this first point up here, point B, 44, 24. Go ahead and write that down. And hopefully your sketch looks a little bit like mine. You won't have graph paper, but You can put the numbers in and let the numbers do the talking. Now, point A, I counted that one too, 8 comma 16. Nice. All right, so now I've got the locations on this distance scale, meter, 1 block per meter. In the x direction, 1 block per meter in the y direction. All right, so how far apart are they? Well, in this distance, in this coordinate system, they do not fall on a horizontal or vertical line. So here's the, there's the line, straight line between point A and point B. So the way to figure out that distance is just to put in, use your right triangle technology. All right. Now, if it's on the surface of the Earth and they're not too far apart, you don't have to take into account the curvature of the Earth. But if you're going from Chicago to from Orlando to Chicago, you definitely also have to take into account the curvature of the Earth. But for just around, campus, just around Orlando, not really. So here, let me back it off. And then you put in your dimensions. Let's do that. The width of that yellow right triangle is 36 meters. And what is that? 44 minus 8. The x-coordinate of point B is 44. The x-coordinate of point A is 8. So 44 minus 8 is 36. So that's the width of that distance, the width of that right triangle. Now the height of it comes from the y-coordinates. 24 for point B and 16 for point A. So the distance, the vertical part of that triangle is 8 meters. And then you go 36 squared plus 8 squared. See, that's 1,360. And hey, you guys, start bringing your calculators to class. We won't be doing it's not like, an engineering class where you're calculating out the wazoo, but we will probably do some simple stuff pretty much every day. So, because I don't know 36 squared off the top of my head, so I have to use a calculator. Now, I know what 8 squared is. That's 64. That's an easy one. Yeah, 1296 plus 64 is 1360. All right, and then you square root that, and you get 36.9. So there's the distance, okay? And in the textbook, there's an appendix on triangles and other shapes that you can read, and if you're feeling a little bit. So here's your calculation here. All right, so 36.9, 36 squared plus 8 squared, 1360. Square root it, and you get 36.9. And there's a few other examples in the textbook in the appendix. This basic Pythagorean theorem and a little bit of trig. Nothing fancy. So that's just the distance there that a crow flies. But that, that's nice on the map. That's the distance a crow flies. But, between point A and point B, if all you know is the endpoints, you haven't specified anything about the actual path. All right, you know where it ends, where it starts, and a lot of times that's all you need to know. But what if it's something like this, a curved path? All right, go ahead and make a curved path, and I'm going to park it down here. All right, so that's a curved path between point A and B. Let's do that. There it is. There's the curved path. And I'm just going to park it down a little bit lower out of the way. All right. But your odometer in your car could do that, or your odometer for your bike could do that, or, your walking app, if you have something like Nike Run or something like that, you can measure distance along a curved path like that. And you know what they do? All that they do is they measure your position and make a bunch of little teeny right triangles and just do a squared plus b squared equals c squared a zillion times for little teeny segments of that path and just add them all up. That's how they do it. Here's a segmented path. What if so what if you're going like this? What if this is what the road network is between point A and B? You have two roads, and you kind of slide on one, then you cut right, and you cut left on another one. And there's cities where you might find roads like that. And there's cities, where you might find roads like the curb path. So if you just know the endpoints, you still don't know everything. Another thing that you want to know is the temporal information. At what point in time is it at point A? At what point in time is it at point B? We don't know that yet. Right? So if you're trying to figure out motion in 2 dimensions, and all you know is the location, you don't know anything about the motion yet because you don't have any time. You don't have any temporal information. All right, so let's post some of that. I just made this part up. Okay, let's just say that at point A, the clock reads 1:22:08 p.m. I just dreamed up a time on the clock, early afternoon. And let's say that whatever this system is, baseball, driver, a crow, let's say that it gets out here to point B at 1:22:47. All right, so now you have your elapsed time. Okay, elapsed time of 39 seconds. So we know as a crow flies 36, so make a note of that. Put a circle around 36.9 for the crow flying distance. And then from this information here, the two clock readings, 39 seconds, elapsed time. So if it is a crow, it's going 36.9 meters in 39 seconds. But if it's on a curved path, you'd have to measure that distance and stuff. And we're just going to do the straight path here. Now here's another factor that you don't know. And this goes back to the issue of the time evolution equations, or the equations of motion. How does the speed change? Because if you hit a baseball straight up, a pop-up, it starts out with a lot of speed, but by the time it goes further up in the air, it loses speed. And then at the very top of the motion, it stops, v equals 0. And then it starts gaining speed on the way back down. The velocity arrow is upward and gets smaller and smaller and smaller. It gets to 0, and then it becomes downward velocity, and it gets bigger and bigger and bigger as it comes back to the Earth. So the velocity is changing. All right, now we don't know anything about that on this path yet. All right, so we have shapes, we have time, we have velocity changes, and so the evolution equations are the things that we want to do. And as I said, for projectile motions, we've got it. So here are the things that we need. We need positions and distances in meters. We need times and elapsed times in seconds. And we need direction at each time and speed at each time. Now you could have a list, and in the textbook I have a kind of a table of positions and stuff for the tortoise and the hare problem, or the fable of the tortoise and the hare. I just gave them some imaginary speeds and distances and stuff. But yeah, the equations of motion, the time evolution equations, you need all that stuff. They encode all this. So you could have a table without an equation, but the equation encodes everything in this thing. So number 3 and the number 4 are basically what is the velocity at each time, at each instant of time. If you know that, you can get everything. All right. So with these informations, you can make out the mathematical backbone, the equations of motion for any of the 3 paths, whether it's the crow flying a straight path, segmented path, going in one direction, changing to a second direction, then to a third direction and arriving at the goal, or the curved path. Now let's keep going with Galileo's ideas of motion. Speed is a quotient. It's a ratio. It's the average time rate of change of position. And that's what this fancy formula shows you. It's a time rate. So in other words, the denominator is about time, and the numerator is the thing that's changing. That's the position. All right, so let's talk about those. First of all, the distance between two events. The symbol delta x means the difference in two x coordinates. So if you're on the crow flying path and constant speed, the change in the x coordinate or the change in the y coordinate, and here's what delta x means. It means x2 minus x1, or x final minus x initial. And students, a delta is always later minus earlier. So x2 is later than x1. xf is later than xi. All right. X final is later than x initial. x2 is later than x1. All right. And so that's the customary orientation of a delta, in this case delta x. All right. So now the other thing is you possibly could be going along the hypotenuse. In that case, you need just the distance along the hypotenuse. So in our case, 36.9 meters for the crow flying. All right. So if you're just going straight along delta x, yeah, you can do that. Or if you're just going straight along delta y, yeah, you can do that. But if you're going along the hypotenuse, if you're kind of going on a slant, just get the hypotenuse, 36.9 in our example. Okay. So, and it's going to be measured in meters. In this class, we're going to try to stay meters, seconds, and kilograms for almost everything. So we're not going to do light years, and we're not going to do feet, yards, miles. We'll talk about miles occasionally. The other thing you need is the elapsed time between two events. So that's the symbol delta t, the difference in the two clock readings. So 122.08 and what was it? 122.08 and 122.047. Yeah, and so that's delta t is equal to t2 minus t1, or sometimes you might like to style it tf minus ti, final minus initial, later minus earlier. That's the way we always do it, and that keeps everything consistent. I mean, we could have done everything in the opposite way, but tf minus ti is the way that we normally do that. So in this example, it's 39 seconds. And so a crow that flies 36.9 meters in 39 seconds, you'd have to say is pretty slow. All right. And so let's do the calculation here. So underline or emphasize 36.9 meters and 39 seconds. All right. So here we go. V is equal to 36.9 meters on top. That's the length of the hypotenuse. So this is the crow. And the crow is slow. 39 seconds. Now, you may say to yourself, Dr. B, how do you know that that's slow? Well, 36.9 meters is about 40 yards. In the NFL, a really fast wide receiver or defensive back or running back can run 40 yards in 4-point-something seconds. 4.5 is considered fast. 4.4 is considered really fast. And there have been guys that have run in 4.1. What was the speed of Shaquem Griffin? Yeah, he ran a wild time last in the combine. What was it? That is sick. I mean, that's like wide receiver times. That's DB times. And I mean, so that, and he's a line. Is he still? He's playing linebacker yeah, in Seattle. Uh, I remember because I remember he made a play the other day in the game in Seattle. So, oh, the stinking Dallas Cowboys won. I hate the Cow. There's two teams I hate are the Cowboys and the Patriots. Question. I just made it up. I just remember when I had the point A and point B, I counted the blocks. I just chose any 2 points on graph paper. I just closed my eyes and chose a couple dots, and then I had to make up a couple. And I just said, well, let's make it 122.08 and 122.47 in the afternoon. 122.08 or 122.47 minus 122.08 total. So the elapsed time is 39 seconds. So this guy's going maybe 40 yards and 39 seconds. That's pretty slow, right? And so it calculated out. Anybody get this? 0.946 meters per second. Yeah. So, and here's something you could jot down in your notes for today. 1 meter per second is about 2.2 miles per hour. All right. Now you walking across campus 2 miles an hour, that's pretty much of a stroll. 4 miles an hour you're cooking. 5 miles an hour you're cooking. You're hustling and bustling. But 2 miles an hour you're just kind of moseying along. And that's about what this crow's doing. He's just kind of moseying on down to his new position. All right, so there's our calculation. Would you guys like homework for the weekend? No? You sure? Because I know homework always cheers students up. No, we don't have any homework this weekend. But let's finish this up. So the distance formula. Now, the distance formula is based on the speed formula, v equals delta x over delta t. So all you do is you cross multiply. You get the delta t cross multiplied to the left side, and you have delta x on the right and v delta t on the left. All right. So if you know the average speed, yeah, you can just go delta x equals v delta t. Distance equals speed times time. All right, and so it's based on that same concept. Now, we're going to stop here, and let me just give you your homework assignment for the weekend. Make sure, if you haven't already, do homework 0 for attendance, and then be alert for the textbook go ahead in discussions. And I'll see you next Tuesday. You're dismissed. Caldwell. Yeah.